Okay, grab a cup of coffee or hot chocolate and get comfortable, and let's learn about diffraction gratings. We've learned about single slit diffraction. In our last lesson it was the Young's double slit, so a two-slit system. And now what we're going to really do is put that together conceptually here. So first, a review of diffraction gratings. The pattern we get from a diffraction grating: a single slit. A single slit is all we're talking about. And because of the light going through here, the little micro regions along here interfere with each other in such a way as to produce this kind of pattern, which you've seen evidence of. This is a diffraction pattern for a single slit. All very good and fine. Hope you're maybe semi-comfortable with that. Now, a double slit. So a double slit, because of two slits, and the point sources interfering with each other, we should get something that looks like this. Generally, we have a narrow little region of variation, and it repeats itself over and over and over and over and over. Oh my gosh, what is all this? All right, that's the kind of pattern that you might determine you would get from a two-slit. And in this particular case, that's what would result if the separation distance D, this D here, is 4 times as much as A. That's what you get. Okay, and as maybe initial validation to that, from here we go 1, 2, 3, 4. And there we're at our first order. All right, in either direction. But in any case, you have not seen that. So when you do the Young's double slit experiment, it doesn't look quite like that. Now these would be the beads that show up on the screen, the bright beads separated by a little dark line. So that makes sense, but you don't see a uniform pattern of those little beads of light along there, do you? No, you don't. And the reason is because A over here is not of infinitesimal width. So A is finite, okay? And then you have diffraction from those slits. In other words, single slit diffraction is what produces this pattern here. Well, you have those slits here as well. So you have the diffraction phenomena taking place at the same time that these two sources here are interfering in a two-source, two-slit interference pattern. So basically, we will have the overlay of the diffraction pattern onto the two-slit pattern. And so here's what it looks like. Here's our diffraction pattern. And overlaid on it is, that's overlaid on the two-slit pattern so that the result looks like this. In other words, the diffraction limits the intensity of the variations of intensity of the two-slit pattern. Two things going on there at the same time. The intensity variations due to diffraction limits the intensity of the double slit pattern. Isn't that awesome? So on the screen, what you'll see is the little beads corresponding to the two-slit pattern, but the strength or the intensity of those beads side by side varies from bright beads to dimmer beads to the beads look like they go away, and then they start getting brighter again, but not as bright as they did in this first region. So it's a little more complicated, but it's just bringing those two ideas together at the same time. Now we're going to extrapolate the idea one more time and consider that instead of a single slit, we have multiple slits, many slits in fact, upon which monochromatic light is impinging. So we have this wave front represented by all these rays hitting the little tiny slits along this region here. So it's combining all this together. And here are rays going in a particular direction. And they are angled at theta from the horizontal. And if we do this little thing, we have this right triangle again as before. And we'll see the same situation holds true here as it does for the 2-slit as far as conceptually. So rays from each slit arriving at a point on the screen will be parallel. All right, what I mean by that is this is really small in dimension compared to, the screen that's over here that it's shining upon, and the dimensions of the pattern showing up there. This whole region along here is really tiny. Okay, it's micrometers. So these rays being parallel to each other will arrive at a point here, but that's basically a point. It's like the same point. So hopefully that makes sense. And they'll produce a bright spot if the path difference between adjacent rays is m lambda, which is equal to d sine of theta. So again, we have d, this is d sine of theta, that's this little angle, or this angle, is this little distance here. So that's d sine of theta. So we have maximum occurring at when d sine of theta is equal to m lambda. All right, m being any whole number, including 0. Rays from each slit will be lambda, one wavelength longer than the previous. So from here to here, the path difference is one wavelength. That's all this is saying. Adjacent rays, the adjacent rays, that's where you'll get maxima occurring. Okay. Now, when we look at a place on the screen from all these rays together, that's just off that point. That's just off from that perfect place where they constructively interfere. We have something taking place that's got just a little bit of difference from how it worked before, but very similar at the same time. All right, so with a 2-slit pattern, if we have a 2 slit patterns, the rays gradually diminish because they're getting out of phase or out of step. So when we look at a 2-slit pattern, the intensity variations occur gradually because of diffraction, as before. So we have a bright spot here, and then as we change, look at different places along the screen, a small angle change is just getting less intense rather slowly until it's totally destructive interference, and gradually increasing to the maximum again, and then gradually decreasing again as we go through these orders because of the way that 2-slit interference occurs. But we have multiple slit interference. So now if the angle is increased a little, the adjacent rays, so we change the angle of all these at the same time, but the adjacent rays are very similar to the same wavelength. I mean, in other words, with just a really small change in the angle, looking at a different place along the screen, a really small angle change isn't going to produce much difference into adjacent rays. In other words, a lot smaller than the theta you see here, where it is perhaps making the bright spot at m is equal to -1 or 1. A small angle change is going to be like just, before going from here to here, the intensity doesn't change very much. But the thing is, there's rays down here as well. And a ray a long ways away, in the same way that cardboard wave demo I did, if I separated the sources by a long distance, then the rate at which the phase changed increased a lot. Hope I'm not using too many words and totally confusing you. But if that angle is changed just a little, there's going to be a ray way down here somewhere where the difference in path length is still really big. You could think of extrapolating this blue line way out like this. So the ray down here, the path length is, I probably shouldn't have shown it going over here, but it's like parallel to that blue ray I'm drawing here with my cursor. Okay, and so that path length would be really big, even with in other words, with a very small change in angle, you can still get constructive or destructive interference happening way down here somewhere. That's the point. So if it's increased a little, the adjacent rays are almost still in phase, but some slits down, or some distance down, a ray that's several down, will cancel that ray. And so all light is eliminated due to pair canceling. It's like almost everywhere along the screen, when you have different places that you're looking at the light energy, you might have these two that are pretty close together and it's almost in phase, but there's always going to be a ray somewhere else that's canceling that one. So the pair canceling occurs almost everywhere, and you end up with a sharp, narrow maxima. And the more of those slits you have, the narrower and sharper the maxima are. Because if you shift it ever so slightly, there's going to be a ray that's canceling. All right, so anyway, with all that explanation, here's what the picture looks like. And it's not perfect because you never have perfectly narrow slits or having the slits be close, so close together, you know, to be infinitesimal. So this, for instance, is like a 7-slit pattern that you get. In other words, you see the cancellation happening significantly everywhere except where the maxima are supposed to be. We got the maxima there, but it doesn't vary, it doesn't diminish gradually, it diminishes rapidly. And the more slits you have, the more rapidly the diminution occurs. And you just have a bright spot followed by darkness, essentially, and then another bright spot. Darkness, another bright spot. If the number of slits is really big, this device is known as a diffraction grating. Diffraction grating. So now the secret is out. Well, let me finish out this lesson by just trying to answer a little bit what diffraction gratings are used for. And a really good answer to that is called spectroscopy. It's the study of light, particularly, light produced by different elements. And this is very useful in astronomy, trying to figure out what's out there. We use spectroscopy to basically spread the light out. It's determining the chemical makeup of matter by observing the distinct wavelengths of light that matter is emitting, typically gases. And that wavelength display is called a spectrum. So I'll give you a brief description. Typically, light from the sun, for instance, is mostly white. It's a pretty good approximation. So if it hits a diffraction grating, it's got all the wavelengths in it. Rays from all the slits are in phase at the center. Okay, so it doesn't matter. So the center will produce a bright white band. But now each color corresponds to a different wavelength. And based on the wavelength, the angle from the diffraction grating to the screen where it's constructive interference, we have the constructive interference. See, that's wavelength specific. The place where it constructively interferes is going to be based on the wavelength, in addition to the other things we just learned. But each wavelength needs its own path difference. I mean, a longer wavelength like red is a higher path difference than blue, which is a shorter wavelength. It requires a shorter path difference. So the angle is likewise different. So at different angles, you see different colors. And that spreads out the colors of light. So when you look at a diffraction grating, you see effectively what you get from a prism, which spreads the light out. You know, dispersion in a prism? Well, diffraction grating spreads out the light because the constructive interference is occurring at different places for the different wavelengths. Woohoo! That's awesome. They can either be transmission types, letting the light through, or reflection types, which reflect the light off of very closely spaced lines or pits, like on a compact disc. All right? Now, the equation is the same for the maxima, whether it's a reflection or a transmission type. And if it's a reflection type, after it reflects off, the light interferes after that point. So it's the same idea, though. Now, just to give you an idea about a typical diffraction grating, there are about 1,000 slits per millimeter. So a millimeter is like a really tiny, thin line. You're going to put 1,000 slits in there. That's the actual dimensionality of these diffraction gratings. So if you want to determine the spacing between the slits, the small d, it'd be the length per slit, and it'd be the length of the whole thing. The length of the region that you're talking about, in which in this case our data says a millimeter has 1,000 slits. So that gives you 1 micrometer of spacing, a micrometer, invisible to the naked eye. But that's perfect kind of dimension for light interference, because light is nanometers, and so that's able to, like a 500 nanometers, half a micrometer. So that is the basics of a diffraction grating. I know this lesson has been a little grueling, and next we will look at a compact disc as a diffraction grating, since that was alluded to, and it's kind of interesting to think about a piece of media like that that's actually a diffraction grating, which isn't what it's designed to be, but it just turns out to be. See you next time.